distribution grid impacts of charging light-duty electric vehicles in Northern California. This is the work that I am doing with Alan Jen in for a grant from the Sloan Foundation in association with the Plug-in Hybrid Electric Vehicle Center in UC Davis. And so there's sort of transportation elements and energy elements. So we'll touch on both of them. And this is still, these are some preliminary results we'll get to by the end of this presentation. So it's just getting to the point where we're getting some cool results. So they're fresh off the press for you guys, as they say. Okay, so the big question is, how will high penetration of PEVs, plug-in electric vehicles, impact the California distribution grid? It's going to be a lot of acronyms. I'll try to go through them if they come up. And relevant to this is, how can the results from California's Distributed Resource Planning, DRP proceedings, be used to analyze future PEV and other DER impacts? So just to clear it up, PEV stands for plug-in electric vehicle, which includes both battery electric vehicles, which are BEV, and plug-in hybrid electric vehicles, which are PHEV. So you got your PEVs and your FEVs and your BEVs. BEVs plus FEVs equals PEVs. Is that clear? It's very complicated. Please interrupt if you have any questions, or it's very weird presenting to a screen, so it's nice to have some human interaction sometimes. Okay, and then the other question is, how do our demand projections compare to the existing projections from utilities such as PG&E? Because they are also very interested in trying to understand how their grid is going to be impacted. So some context. EV charging is already affecting the grid at both the local level and the wholesale level. We have around 500,000 plug-in vehicles in California right now, maybe more than that. And the governor's goal, Jerry Brown's goal, was to have 5 million electric vehicles by 2030. So this is rapidly expanding, even though there's potentially some hiccups now with COVID in terms of sales of PEVs. So utilities, the state, and electric vehicle service equipment, EVSE, which just means like charging infrastructure, companies are all working together to expand this infrastructure, and people are definitely thinking about the different types of grid impacts. So what kind of grid impacts do we talk about? Well, you could have an overall like effect on the system peak or a system load shape at the CAISO level. You could also have individual transformers, like overloading if you have too many cars in one block. Or you could have these intermediate effects, which are feeder and substation level impacts. Okay, so what does that mean? So this is like a basic distribution grid. You guys can see the mouse, I think. Let me know if you can't. So you got your power coming in from some faraway power plant. This is the kind of standard way it works. Comes into the substation, and then everything downstream of the substation is what I'm calling a feeder. So, or feeder means one of the circuits that serves a city coming out of a substation. So for example, in Davis, there's 12 of these. And then off of the feeder, then you have the individual transformers that go to different houses. So this is how the grid kind of worked. It's pretty simple. Power flows downstream to your end user. Everyone knows that now things are changing. We've got all these batteries in here. Oh, look, a solar panel. We got power going both directions now. What's up with that? And then you add all these green electric vehicles, and they're plugging in, and it's getting a little chaotic. It's getting a little wild at the grid edge. And so because of that, distribution resource planning is cool again. What used to be just kind of super simple engineering, or not simple, but straightforward, I should say, is now more of a matter of public interest because there's solar developers that are trying to figure out, okay, what are the limitations of where we can put solar, and the PUC, Public Utilities Commission, is mandated that the utilities in California kind of like be a little more transparent about the distribution grid. We have all this great data from CAISO about the transmission, about wholesale power, but distribution system is sometimes more confusing and hard to access data-wise. So this is a map that I downloaded onto GIS from publicly available data sources, and this is just kind of a cool image of all the different substations, all the different distribution grids in the Bay Area. So each color represents a different substation, or represents the feeders served by one of the substations, which is in black. And I just think it's a pretty graph. But if you zoom in, you can start to see like the actual power of this data set that the PUC had mandated that utilities make public. So the data set includes shape files of all these feeders. So this is Davis, and all the blue here is served by the same substation, and then you see a different substation up in Plainfield, one in Winters, one in West Sacramento, and then over here in the right is SMUD territory, so it's not covered by PG&E territory. So we can zoom in further. Let's zoom in further, and we look at Davis itself, and this data shows one individual feeder, for example, in this turquoise, feeder 1103. So there's 12 feeders that serve Davis. This is one of them, and as you can see, it can be kind of random, chaotic, which neighborhoods it serves. It's not exactly the Dutch planning, New York City. It's a bit chaotic. As different subdevelopments get added, it gets extended, etc. But this data set from PG&E has something really cool, which is it has these load profiles available, which is their estimated sense of what a typical high load and low load day looks like for each feeder, about 2/3 of their feeders across California, which is about 2,000 feeders total. Some of them have data redacted for privacy reasons if there's not a lot of customers, but this yellow line is what we use, what I'm using, and that's the high load. So like on a kind of typical high load scenario day, this is a high load day in June, high load day in July, high load day in August, high load day in September. So there's one data point for every hour of a single representative day per month. A little bit confusing, but there's essentially 48 data points per month. And so you can actually get a sense of typical kind of baseline load on these individual feeders. And so you also have other data sets that I started looking at called the Grid Needs Assessment data set. And this one actually tells you the capacity of the feeder and also other information about whether they think it's going to need an upgrade in the future and other things at the feeder level, which come in handy. And so you can start to look at this PG&E data set and start to learn some interesting things about the grid itself. So first of all, this is a map of the distribution planning regions that PG&E has. So you have the Bay Area, Central Coast, Central Valley, and Northern area. And you can actually just right off the bat do some interesting just exploratory data analysis to see like how many circuits, and by circuit I mean feeder, those are interchangeable, and I apologize for not picking one and sticking to it. And then you can also see what time of the year and what time of the day we hit peak load. And so on these individual circuits. So in the Central Valley, all the feeders are peaking in the summer, which is red, and most of them are peaking at 17 o'clock, which by that I mean 5 p.m. For those not in the military. But in contrast, if you look in the Bay Area or the Central Coast, you actually have a lot of winter peaking circuits. So meaning their actual peak load comes in the winter due to potentially heating load. But oftentimes the peak is also around 5 or 6 p.m. here. So this is looking at their projections for expected new peak coincident EV load. Okay, so what does that mean? So basically, this is the assessment of how much electric vehicle load PG&E expects in each feeder, how much of new electric vehicle load they expect to coincide with the existing peak time. So for the Bay Area in 2022, they expect the median circuit. So maybe that's just like you're a circuit with an average number of EV users. They expect there to be 60 kilowatts of EV charging on average that coincides with the already existing electrical peak. So this is something that we're kind of trying to assess, and then so these two graphs we're kind of trying to model ourselves and compare. So this graph is essentially on the x-axis we have the amount of EV intensity, so peak load, proportion of peak load from new EV load. This is, so something over here is going to have like 6% of projected peak load from EV charging. And then over here we have the actual circuit peak loading. So what PG&E has in their models as what percent of the capacity of the feeder that each feeder hits. So for example, over here we have, this would be like a feeder that has a ton of EVs modeled in it. So 6% of that peak load is EVs, is from charging. And it's also kind of overloaded already. So it's at 1.25. So that means like when it hits that summer peak or winter peak, on certain days, it might go 25% over its capacity. And that happens. There's plenty of places where the grid already goes over the capacity. It doesn't blow up. It just loses longevity, starts overheating. It's not ideal, but it does happen. And then in orange, we have whether or not this feeder is already in the database of PG&E's grid needs assessment. So what does that mean? It just means that they're watching it, they're expecting to upgrade it. So we can see that there's a lot of these EV intensive feeders, and there's some EV intensive feeders they're expecting, and there's a lot of places where they're not expecting a lot of EVs. And so we're kind of interested in seeing how does our model compare to this, and are they missing some, like are there places where there's going to be more EVs than they're modeling and more grid impact. So they use this model to get load profile, which I won't go into. It's a bit of a black box. So we're kind of trying to recreate this model and use some of the existing modeling capability from UC Davis. So we're combining a big study from the PHEV Center on real charging data. It's called the EVMT project. So we're using load profiles that are just bootstrapped from real users, real EV chargers, where there's actual loggers on the cars. And then we try to map, so that's like 21,000 charge events that we're mapping from, that we're sampling from for battery electric and 36,000 for plug-in hybrid. So basically, we use my colleague Adam Davis's EV toolbox model, which basically is a way to map the load, expected EV load onto individual census block groups. So I'm running out of time, so I'm going to skip forward. I know I didn't explain the methodology well. You can ask me questions. Basically, we also adjusted for the fact that our sampling data includes a lot of Nissan Leafs. It mostly includes Nissan Leafs and Teslas, and it's from a few years ago, so we kind of adjusted it to try to figure out, okay, if people are preferring bigger batteries now, then we should weight the samples of the Teslas a little more than the Leafs, based on the sales of current battery electric vehicles. So if you just basically, I'm going to skip this one. Okay. So basically, you sample all these existing charging profiles from real BEV users, and you get this kind of load profile. And this is starting at midnight and going the middle of the day, and then ramping up starting around 10 o'clock. And so what we see is that in the data from people charging so far, they charge in the evening. This is kind of the typical, they come home from work and often might set a timer on their EV or plug it in before they go to bed. And basically what we've done is tried to map the load, expected EV load for each individual, expected number of EVs for each individual census block group, and then map them spatially to an individual feeder. And so that's a bit tricky, spatial mapping, but the bottom line is then you can run a model and say, okay, in this scenario, we expect this particular feeder in San Jose to have 484 BEVs, which this is and 140 PHEVs. And so this is like in a scenario where there's 3 million PEVs in all of California. So then we can compare it to we can add it on to the existing load. So the black line is the existing load profile of this feeder in San Jose. The red line is the distribution of samples, so for EV charging according to our profiles. Okay, so does anyone notice anything interesting about this kind of effect on this feeder load profile? Anybody? It's a hard time.
Everyone's quiet. Feel free to chat. Oh, Steve Schaefer said it shifted earlier.
What do you mean? The peak load or the? Yeah, so it's starting to affect the actual peak time. So if before the black line, the peak time was about around 8 o'clock, well, we're worried about the EV charging that's happening at 8 o'clock, but it turns out, you know, if we look at when people are mostly charging their cars right now, then we actually might need to start worrying about the 10 and 11 o'clock time, so that the peak time might actually shift later in the day as a lot more EVs come in. So this is a scenario with 3 million cars in California in September for this feeder, and then this is one with 5 million cars. So just more cars, and you start to get above the feeder limit. So these are the kind of things we're interested in. Oh, geez, dang, it ran out of time already. And basically, it's pretty interesting. If you look at the East Bay, all the feeders, this is the time of day when the peak happens. So without very many EVs, the peak mostly happens at 6 or 7 p.m. And as you add more and more EVs, you start to see that the peak time actually starts to move. Now you have some peaks at 11 p.m. Now you have actually as many at 11 p.m. as 6 p.m. With 6 million BEVs. And there's a couple, okay, I just have to show you this graph because it's crazy, and then I'll stop talking. So this is showing, again, as you add more and more BEVs, 1 million, 2 million, 3 million, this is just some feeders in the Bay Area. You start to see, this is the same graph except with our data from the EV intensity on the x-axis and the peak loading. And so you start to see that as you add more BEVs, you have more EV intensive feeders, obviously. And again, it's just some that have a lot of EV charging, as we'd expect. And then you start to see that these pink dots appear, which means that the peak time is shifting from the blue, which is like 6 p.m., to the pink, which is 10 or 11 p.m. So yeah, I'll stop here. And basically the bottom line is that we got to start thinking about the actual, both the coincident peak load, so when charging happens at the 6 or 7 p.m. existing peak, but also we got to start thinking about, okay, what does this mean for when the peak itself is going to happen at the local level? And I'm excited to continue this research. Thank you very much.
Thanks, Jake. Really interesting. You have a couple questions here. I'm going to unmute Steve. I hope I'm saying it right. Steve Schaefer first. He had a question for you. There you go, Steve. Oh, Steve may have stepped away. So let me get to David Hungerford. He had a question for you. Let's see if he's around. All right, David, you're unmuted.
I'm here. I was trying to unmute my phone too.
Oh, got it.
Yeah, I was just wondering how malleable you think charging behavior might be if the rate structure were changed to incent people to charge at different times. Right now, we have most of the car chargers are not really they don't have much dynamic capability. You can like set them to start charging at a particular time, or you can plug in before you go to bed, but you can't really tell your car to charge when the prices are lower or when there's more renewables available. How malleable do you think that could be, and how would that affect your feeder analysis?
Yeah, it's a great question. So this is PG&E's EV rates. They have two different time of use EV rates, one with a sharper peak price and one with a less sharp. And so I think the question, there's a couple questions. One is, what is the rate incentive? What is the incentive based on? Is it based on local impacts, or is it based on desire to get low carbon electricity? And those are different questions, right? Because you might incentivize daytime charging for if you're trying to get solar, but if you're trying to avoid local distribution impacts, the most important thing is just to avoid that peak, and then charging in the night is sort of the ideal outcome for that. So that's one question. Right now, like they are, doing that, but not everyone enrolls in those rates, especially people that don't, own, that aren't charging like in their own private garage. There's some evidence that a lot of people, because the price differences aren't that high, there's some evidence that people aren't actually, charging based on the rate structure as much as we would like to think, because the price differences aren't necessarily that huge, especially with the segment of the population that owns EVs, which are more affluent people so far. So yeah, I think that ideally we can use rates to affect when people charge, but one challenge is that the distribution grid impacts are different from region to region within PG&E, and so then you'd start getting into like super hyper localized rates or programs if you want to avoid grid impacts on a local level, and that becomes a lot harder to implement.
All right, we have another couple questions. We'll take maybe one more now, and then we'll switch to Devon, and we'll have time at the end as well to continue asking questions. This is from, let's see, Alan Meyer. I can read it, and then I'll unmute you, Alan, in case you wanted to follow up with additional questions. Let's see. So Alan asked, do you know if the voltage sagged in the distribution system in areas with high EV penetration?
The short answer is we don't have the data to measure like grid impact on voltage sag. They have some data showing like depending on the type, the circuit topology, then some places certainly will have that sag if a lot of people are charging at the end of a long line where there's not a lot of interconnection to other circuits. But the data that we're using for this is a little bit higher level, and it's just basically adding load and checking the peak for the feeders. It's not necessarily getting to the some of those other issues like voltage regulation. However, I certainly know the utilities are a little bit concerned in some, especially in certain areas. But yeah, we don't have the granularity to look at that very easily. But thank you for that question. It's very interesting.
Hi everyone, I'm Devon. I'm a second-year master's student, and I'm going to talk to you a little bit today about a project I've been working on for the last year. And it was concerning demand flexibility with the UC Davis Central chilled water plant. So outline for this presentation, first we'll go over kind of motivation and background, and then we need to go over our UC Davis electricity rate structure. Then I'll give you a little bit of introduction to what our chilled water system looks like and what kind of equipment is involved. And then we'll go over the load profile optimization, proxy demand response program optimization, and then the description of kind of what's next. So the motivation that I have is in flattening the duck. Can everybody hear me?
Yep, you sound good.
Okay, I just got a notification that it said, yeah, I might not. Okay, so as we've learned in California, achieving a zero carbon grid is about much more than just installing renewable generation and hoping for the best. And so we must also use energy efficiently, and what it means to use energy efficiently is changing. Now it's not only the need to reduce wasted energy or install better equipment, we also need to be smart about usage decisions, kind of in line with what Jake just talked about. And as CEC Commissioner Andrew McAllister said yesterday, buildings have to be part of the solution to achieve a zero carbon grid. And when I first came to UC Davis and was introduced to the idea of demand response, I thought it was a really powerful idea and important potential resource, but also that it sounds really complicated and something that is worth studying. Okay, so I asked what could we do at UC Davis? And the greatest opportunity at UC Davis lies in our chilled water system, because it it represents the largest load with the least amount of switches, essentially. So, and then additionally, we have a thermal energy storage tank, so which operates like a giant battery. And so with this in mind, what opportunity do we have to use our load flexibility? What benefit does this provide to campus? And what benefit could this also be to the greater electricity system? So the picture that you're looking at is the chilled water loop, and all the dots represent the different buildings that are connected. And you can also, well, we'll go over this in a little while. So thinking about what flexible demand means, what different types of activities could we try? So one is load profile optimization, where you just adjust your load to meet a certain objective, and that could be the least amount of cost or the least amount of carbon intensity associated with your usage. There's also retail demand response programs, where you get incentivized to, but it kind of depends on the program, but you get incentivized to be on standby and then reduce your demand when you receive a signal from the utility. Or there's wholesale demand response programs, which which kind of vary widely, but I will describe to you what it's like in CAISO's territory later on in the presentation. So first we had to answer the question, what is our electricity rate structure? And a year ago, we didn't know much about it. We knew that we paid about $12 million per year, and that worked out to about 7 cents per kilowatt. But this is definitely not the entire story. So we had to do some kind of research and investigation into this, and UC Davis purchases electricity from WAPA, the Western Area Power Administration, and that's a government entity that is a nonprofit, and it was originally tasked with selling all of the country's hydropower from our dams, but they provide all of the power for UC Davis, and we're charged based on our consumption pattern. What we use in comparison to the portfolio we are a part of. So WAPA makes purchase decisions on behalf of a group of customers, and we are one of them. And then what purchase decisions or long-term contracts WAPA has made already, and then how much hydropower, and I'll also refer to this as base resource, is available. So our electricity costs can be broken up broadly into 3 main categories. Our energy transactions. So this is all the kind of balancing of UC Davis's energy usage with generators around the electricity system. The operational costs, so getting it from whatever generator to UC Davis. And then planning costs. And the bulk of our cost is from energy transactions, and this also represents the cost that is most fluctuating. So our energy transactions can be further divided into 3 main categories. The top 2 equations represent the CAISO market costs. So the first term is the first term is our scheduled load. So WAPA is our scheduling coordinator, and they have to submit a schedule to CAISO, and that is paid at the day ahead price. And then our unstructured deviation, this is the difference between our scheduled and metered load. And then our energy contracts, and these can be either multi-year, multi-month, or just single day purchases between WAPA and a specific generator or power purchaser. And then the base resource transactions, which is the benefit we receive from being able to sell our hydropower resources. So it's important to understand all this, but what we realized is that it's really difficult to know all of this stuff in advance to inform our decisions about what we should do in the future. So we did an analysis to just see what our purchases look like on top of our load profile. And what I apologize for kind of this graph, and it's not very pretty, but what's important to take away from this is the purple is represents CAISO market transactions, or CAISO market exposure, I guess. The green represents forward purchases, and the blue represents hydropower purchases and sales. And we're always at least somewhat exposed to CAISO market prices. And the other thing that's a takeaway about this is I chose May 2018 because that was a big hydropower month. So this is one of the months where we would be getting the least amount of kind of energy just procured from the wholesale market. And then this graph just shows in some months that that component of our cost is a lot. So in sum, what we learned from the electricity rate investigation is that almost all the time, the last in electricity is priced at the day-ahead market rate. And then also we learned that PG&E is not our load serving entity, so we are not eligible for any retail demand response programs, but we are eligible to participate in CAISO's Proxy demand response program. So that narrows down kind of what activities we should target. And first I'm going to talk to you about the load profile optimization. So to do that, you need to understand the chilled water system. So we have 8 chillers, and each chiller runs about 1.5 to 2 megawatts. It can produce 18,000 tons of chilled water, and at the peak, the system can cause or can draw over 10 megawatts. This cost is about $2 million annually, and we have a 5 million gallon thermal energy storage tank, which can hold 40 to 50,000 ton hours, depending on the campus loop delta T. And so this graph shows our total campus electricity, and in green, our chilled water system electricity usage in red, and then the electricity rate in dashed orange. And what you can see is that our peak chilled water electricity demand coincides with the peak rate. And so this means there's a lot of opportunity for optimizing the load profile. This is another kind of representation of that, but the red this time is showing the dispatch of the tank. And so what you can see is that we're dispatching unoptimally too. We're dispatching when the price is pretty low, and beginning to start charging when the price goes really high. And so the question is, if we use tests better, how much of this peak price can we avoid? So optimization program developed by some chemical engineering grad student, Gustavo Campos. He wrote a mixed integer linear program that takes in our chilled water demand forecast, our day-ahead market rate, and then the outside air wet bulb temperature forecast, and then makes decisions on how many chillers and which chillers should be on and off, and then what how much of that production should go to the tank or come out of the tank. And then you also need real-time inputs, which are what's the current tank capacity, what's the chilled water return temperature, and which chillers are currently on and off, because you also want to minimize how many times you turn on or off a chiller. So this is not a great looking slide, but it shows you how the optimization can be interpreted or used by a plant operator. So this top graph shows you what the optimization recommends. So after this dashed line, that's the future, that's the next day ahead, and it says when to turn on a particular chiller. And then you can see like the optimization compared to what actually happened. And then you can see the prediction of what the thermal energy storage tank capacity should be compared to what it actually was. And so using this program, our estimate is that we could save $300,000 a year. Okay, and so then what if instead of load profile optimization, we did wholesale demand response? So first you have to understand how demand response, the proxy demand response program works. And what it is a market product that allows loads to bid in as supply. So you're essentially a proxy generator, and you earn the same amount that a generator would at your particular grid location. So a curtailment service provider will submit a bid for the hour or multiple hours that you are willing to participate and the price at which you need in order to curtail. And then if your bid is accepted, your day ahead schedule is updated to reflect your commitment. This is how it works in a given kind of event. You submit your bid 10 a.m. the day before, and then market results are published at 1 p.m. the day before. So if you are awarded a demand response event, then you'll know then and be able to plan accordingly after that. And then after your event happens, then your the settlements process calculates how much you should be paid, which is a comparison of your baseline to how well you performed. And I just talked about that. So how does a baseline work? You need to look, you generate a baseline basis, and you can only use the previous 45 calendar days, and then you try to get up to 10, but you can use as few as 5 days, and you need like days. So if it's a weekday, then you need to look at a weekday in your baseline, and if it's a weekend, then you need to look at a weekend. And then your baseline is calculated just on the simple average of those days in your basis, and then your event day adjustment is using the 3 hours starting at like T-4 to T-1, and it will adjust your baseline plus or minus 20%. So the main thing that's important is that you can only look at 45 days in the past to find days to put into your baseline calculation. And so that's important for figuring out how much proxy demand response can be worth I'm kind of running out of time, but so this is kind of the procedure we used in order to estimate the value of PDR. You want to participate when the day-ahead price is high. You want to participate when the daily peak price is significantly greater than the average price that day, because you don't want to put in too much work if you're only going to shift your load into hours that are similarly expensive to the one you're shifting out of. And you also want your expected demand to be high so that you have potential to reduce. The constraints are that the campus chilled water demand must be met, that there's enough capacity in the tank to provide the opportunity to curtail, and that the test discharge rate doesn't exceed maximum. You also want to avoid degrading or distorting your baseline, so try to so don't participate more than the number of days you have to add to your basis for your baseline calculation. So this is the results of that study. The total annual savings was about 87,000. We would have participated in 162 in PDR 162 days. The events would have been from 1 to 6 hours long, but most are 1 or 2 hours. So sorry, this top graph shows the curtailed megawatt hours, and then the bottom graph shows you how long you would have had to curtail that amount. But that was a study done in the kind of assuming we had perfect information. So what would we do, or how do we develop a strategy for the future? And that's kind of what we're working on now, but also what about integrating both options, having your load profile optimized to a certain extent, but then adding some additional potential to have flexibility to participate in wholesale PDR. So that's the work that I'm still developing and working on, and that's having an optimization program that does both load shifting and proxy demand response strategy, and then also evaluating it not only in the terms of dollars saved, but also avoided carbon. And that's all.
Great. Thanks, Devon. So if you have a question for Devon, go ahead and type your name in the chat box, and I will go ahead and unmute you. Let's see. So I'll ask this question for Steve, since I don't think he has audio. Are you analyzing the potential of expanding TES capacity? Is there any excess chiller capacity?
We're not assessing the potential to expand test capacity because we don't plan to do any construction on the tank. However, you can improve the tank's capacity if you improve delta T on campus. So if you improve how well the buildings are exchanging heat with the chilled water so that the return temperature is higher, then and the differential between like the water stored in the tank is greater, but that wasn't included in this analysis.
All right, and I have a question from Dwight, which I'll read, and then go ahead and mute you if you have audio, Dwight, so you can follow up. Did you speak with the system operators about your findings, and what was their response?
I haven't spoken with the system operators about our findings, but we did ask them a lot about how the specifics of the PDR program works. But yeah, they have not provided a response on these findings.
And it looks like, Dwight, can you have audio there?
I do. Can you hear me?
Okay. Yes.
Yeah, so my second question was, is the system currently fully automated and pre-programmed for daily operations? How do they do it currently?
Yeah, so our plant is not, is fairly old, and so it's not automated really much at all. And so this is a recommended schedule for the operators to take into account, and then they make the ultimate decisions of when to turn on and off the chiller.
So it sounds like perhaps they need some updated controls to actually implement a more sophisticated strategy to take advantage of the findings that you've pointed out here.
Yeah, that's definitely true.
Excellent research, really interesting. I graduated from Davis in 1973, and I'm fond of thinking about the campus. I come back once in a while. I work at Schmidt in the research group here, so I found both of your presentations very good, and I'm really impressed with the level of investigation and analysis that you've done.
Well, thank you very much. And
You bet.
I'll say thank you for Jake too. I don't know.
You bet.
Yeah. So glad you could join us, Dwight. And let's see, we have a question from Robert. I don't know, Robert, if you have sound. Let's see if I can unmute you. I don't think I can. So I will read Robert's question. Since the choice of what day hour to participate in PDR impacts the baseline of future baseline calculations, do you plan to incorporate that into your optimization in the future?
Yes, definitely.